VC dimension. Let us say we have a data set containing n points. These n points can be labeled in 2 to the power n ways as positive and negative. Therefore, 2 to the power n different learning problems can be defined by n data points. If for any of these problems we can find hypothesis H belongs to H that separates the positive examples from negative examples, then we say H shatters n points. That is, any learning problem definable by n examples can be learned with no error by a hypothesis drawn from H. The maximum number of points that can be shattered by H is actually called the VC dimension. Vapnik-Sharvonanki's dimension of H is denoted as VCH, and it measures the capacity of H. In this figure, we can see that an axis-aligned rectangle can shatter 4 points in 2 dimensions. Then VCH, when H is the hypothesis class of axis-aligned rectangles in 2 dimensions, is 4. In calculating the VC dimension, it is enough that we find 4 points as we found in this diagram that can be shattered. It is not necessary that we will be able to shatter any 4 points in 2 dimensions. For example, 4 points placed on a line cannot be shattered by rectangles. However, we cannot place 5 points in 2 dimensions anywhere such that a rectangle can separate the positive and the negative examples for all possible labelings. Probably approximately correct learning, that is PAC. Given a class C and examples drawn from unknown but fixed probability distribution Px, we want to find the number of examples n such that the probability at least 1 minus delta, the hypothesis H, has an error at most epsilon. In our case, because S is the tightest possible rectangle, the error between H equals to S and C is the sum of the 4 rectangular strips as being seen in this figure. We would like to make sure that the probability of a positive example falling in here and causing an error is at most epsilon. For any of these strips, if we guarantee that the probability is upper bounded by at most epsilon by 4, the probability that we miss a strip is 1 minus epsilon by 4. Probability that n instances miss a strip is this. Probability that n instances misses 4 strip is 4 multiplied by this, and probability that n instances misses 4 strips has to be less than delta, and 1 minus x less than equals to exponent of negative x. For exponent of negative epsilon n by 4 has to be less than equals to delta, and n greater than equals to 4 by epsilon log of 4 by delta. The difference between H and C is the sum of the rectangular strip, one of which is shaded as seen in this figure. Noise and model complexity. Noise is any unwanted anomaly in the data, and due to noise, the class may be more difficult to learn, and zero errors may be infeasible with the simple hypothesis class. As can be seen in the figure, when there is noise, there is not a simple boundary between the positive and the negative instances, and to separate them, one needs a complicated hypothesis that corresponds to a hypothesis class with larger capacity. A rectangle can be defined by four numbers. But to define a more complicated shape, one needs a more complex model with a much larger number of parameters. With a complex model, one can make a perfect feed to the data and attain zero errors. See the wiggy shape in this figure. Another possibility is to keep the model simple and allow some errors. See the rectangle in this figure. Using simple rectangle, unless there is a training error which is much bigger, makes more sense because of the following. Simpler to use makes lower computational complexity, easier to train makes lower space complexity, easier to explain is more interpretable, generalizes better, provides lower variance in the case of Occam's razor, which states that simpler explanations are more plausible and any unnecessary complexity should be shaved off. Multiple classes. In our examples of learning a family car, we have positive examples belonging to the class family car and the negative examples belonging to all other cars. This is two-class problem. In general case, we have K classes denoted as Ci, where I equals to 1 to K, and an input instance belongs to one and exactly one of them. The training set is now of the form x equals to x to the power t, comma r to the power t in the limit of t n, where t equals to 1. This R has k dimensions and Ri to the power t is equals to 1 if xt belongs to Ci and Ri to the power t is equals to 0 if xt belongs to Cj, where j does not belongs to I. From the figure, we can see there are three classes: family car, sports car, and luxury sedan. There are three hypotheses induced, each one covering the instances of one class and leaving outside the instances of other two classes. Now this question mark area is known as reject region, where no or more than one class is chosen. In machine learning, for classification, we would like to learn the boundary separating the instances from one class from the instances of other classes. Thus, we view our K-class classification problem as K2 class problem. The training example belonging to Ci are the positive instances of hypothesis Hi, and the examples of all other classes are the negative instances of Hi. Thus, the K-class problem, we have K hypothesis to learn such that Hi x to the power t equals to 1 if this xt belongs to Ci and Hi of x to the power t is equals to 0 if xt belongs to Cj where j does not belong to I. Here hix is where I belongs to 1 to k.